All right, so good morning again. The second talk of the morning session will be by Sepideh Mahabadi from Microsoft Research, and she will tell us everything about corsets and applications. Yeah.
Thank you, Peter. Yeah, thanks to the organizers. So I'm going to tell you about corsets and their application to design sublinear algorithms. Okay, so I'll start with some definition of the corsets, then tell you some algorithms for constructing them, then move on the second part of the talk to composable corsets, which is a variant of corsets that allows you to design algorithms for other massive data models of computation, and tell you some algorithms in that region. Okay, so what are corsets? So corset is one of the many data summarization techniques. For example, you might have heard of dimensionality reduction, sketches, linear sketches that Andrew told us about, mergeable summaries, and so on. So corset is also one of these summarization techniques. So what is particular about corsets is that they should be a subset of the data. Okay, so the main property of the corset is that it's a subset of the data. Okay, it's a small subset of the data. And why do we care about it? Because sometimes we want to preserve our actual data, okay? The type of the data that we have. So in the summary, maybe we want to find a set of representatives that are from the actual data that we originally had. Okay, so more formally, corsets were initially defined by Agarwal, Harpelet, and Varadarjan in 2005. Corset is a small subset of the data that somehow represents the data very well. So what do we mean by representing well? It means that if we have a problem that we would like to solve on our data set, then a small subset of it, we say is a corset or is a good corset if solving the problem over this small subset gives us a good approximation for if we wanted to solve the problem over the whole data set. So for example, one way to formalize it is that maybe we have a function f that we want to optimize on our original data set. Then if we just optimize the function f over this small subset, then if this gives us a factor alpha approximation, we will say that this is an alpha approximate corset. Any question from the definition of corset? Okay. For example, suppose that you want to preserve the diameter of the points. So we know that the 2 points from a set of points that is furthest away from each other always lie on the convex hull. Therefore, the points that are on the convex hull of a set of points is an exact corset for the diameter. Okay? And but the problem with this corset is that the size of the convex hull itself could be quite large. Okay? So here we're looking for a small subset of the original data set that preserves some property. And I want to mention that the corsets are task-specific, meaning that for different problems or different properties that we want to preserve, or different problems or optimization problems, the set that we are looking for might be different. The algorithms to find them might be different. Okay, and also I want to say that corsets are generic notions, meaning that many variants of corsets exist. For example, we have weak corsets that only preserve the value of the optimal solution, and strong corsets where it preserves the value of any solution. Okay. Sometimes we allow the corset to be a weighted subset of the data as opposed to just a subset of the data. Sometimes in some variations or some works that deviate slightly from the main definition, we allow some additional information to also be kept within this along with this subset. Okay. So why are corsets useful to design sublinear algorithms? So it's clear that once you reduce the size of the data, then basically an algorithm that would have taken much longer time now would take a much smaller time to be run on this small subset. It's good for storage of the data. So now you need much smaller storage to store this data, less communication, and also as I'll say earlier, if it has some additional composability property, it can be used to design streaming algorithms, distributed MapReduce algorithms, and so on. Okay, so we'll talk about this later. Okay, so what problems are interesting in this regime? So traditionally, the problems that need to handle large amounts of data, that need to work with large amounts of data, are interesting in the corset settings. And originally, the corsets were designed in the context of geometric problems. For example, you have a data set of points, and you want to preserve some properties of this data set, for example, the diameter or the kth largest distance, and so on. Or basically some statistics about the smallest object of a certain type that encloses your point set. Okay? For example, what is the radius of the smallest ball containing the point, or the smallest slab containing the points, and so on. So it's important in the context of shape fitting. So for example, you might want to find out what is the best subspace that all the points lie on, approximately. And then, like another class of problems that courses have been studied quite a lot was the clustering problems. Again, here you have a large data set of points. You want to cluster them into K cluster. And now to compute the clustering size, you might want to reduce the size of the data set that you initially have. Another problem is diversity and coverage maximization problems. So again, here you have a large data set. You would like to find a small subset of your data such that it preserves the diversity of the original data set. Okay. Again, this problem has applications in summarization, search, and so on.
Sorry, so for clustering, I'm assuming you're doing some kind of partition.
So for the clustering itself or for the corset?
So what exactly is an example of a corset for, say?
It will go over it. Yeah. Okay, and I also want to mention that in the context of graph problems, corsets have also been considered. If you think about it, the spanners themselves are a type of corsets, right? It's a smaller number of edges from the original graph that preserves the minimum, the shortest distances between all pairs of points. Okay, so in some sense, spanners are also a corset that preserve shortest distances. Corsets are explicitly designed for example, matching, vertex cover, and for many other problems like we can think about corsets, or in terms of corsets as well. Okay, so with that, let's look at some simple and then maybe more generic corset construction algorithms. So directional width is one of the original problems that were studied in the context of corsets. So given a set of points and a direction u, we say the directional width of the point set in direction u is basically the length, the distance of the the most extreme point in the direction u minus the least extreme point in the direction u once projected onto u. So basically, more precisely, the maximum inner product of p with u minus the minimum. Okay, so if you think about, if you look at it pictorially, this is what you are measuring. Okay, and yeah. Let me also mention that the overall width of a point set is the minimum directional width over all possible directions. Okay, and again, why people care about it is that they want to say if their data set lies approximately on a hyperplane, all lie on a hyperplane or not. Okay, so. So here, what's the goal? The goal is to find a small subset of the data such that it preserves this width or directional width with respect to all directions that's going to come on later. Okay. So a simple algorithm is the following. If we just want to preserve the width of this point set along this direction, you can just keep the point that has the maximum projection in that direction and the point that has the minimum projection in that direction, okay, the two most extreme points. And then in order to compute the corset, you can just impose an epsilon net on the all possible directions, and for each of those directions, you can just keep the most extreme and least extreme points in those directions. Okay? So 2 points per direction, size of this epsilon net is 1 over epsilon to the d minus 1, so the size of the corset will be the same. Okay, So no matter how many points you initially have, like n could be much larger than this number, you can always reduce the number down to this. And under some fatness condition, meaning that if the overall width of the point set is pretty small, you can preserve this directional width and width up to a factor of 1 plus epsilon. Any questions? So now let's look at some clustering problems and corsets for clustering. I should also mention that this part uses the lectures by Dan Feldman. So if you want, you can also watch them if you want to know more. Okay, so maybe like one of the simplest problems for clustering is just one center. So in one center, you just want to find a point that approximates the best your data. Okay. So basically, and a corset for one center is the following. So you want to compute a small subset, S, of your data set that later on, whatever query comes, you can approximate from this corset the maximum distance to all the points in a data set. Okay? So suppose this is your query. What is the maximum distance to all the points that you have in your data set? So basically, this is the distance. You want to find a small subset such that, and you want to do it in advance, not after seeing the query, such that basically for any query point that comes, the maximum distance of the query to this small subset is not much smaller than the maximum distance of the query to the original point set. And this is basically the one center cost. So how well does this center approximate your whole point set? So any question from the definition of the one center problem, or like what is a corset for one center problem? Okay. So here there's a very simple algorithm that constructs a corset of only size 2 with a constant factor approximation. So how is the corset? So what does it mean? It means that you can reduce the size of the dataset from n down to only 2 while preserving this value for any possible query that could come. Okay? So the algorithm is very simple. Just pick an arbitrary point P1, and then at the second iteration, just pick the point P2 that is furthest away from P1. So what do we know? We know that all the points in the dataset lie within this ball of radius r, where r is the distance between P1 and P2. And why is this a good corset or a constant factor corset? Well, for any query point, we know that its distance to either P1 or P2 should be larger than r over 2, right? And then if the query, for example, lies inside of this ball, we know that in the original point set, the distance of query to any point could not be larger than the distance of query to P1 plus r. So we get a factor, so we get that the distance of the query to the original point set cannot be larger than 2r, so we get a constant factor approximation. If the query is outside of the ball, a similar argument works. Okay, so basically this simple algorithm gives us a corset of size 2 with a constant factor approximation. And in fact, if you want to look at the k-center cost, a simple algorithm, a similar algorithm would also work. So what is a k-center cost? Again, I have a point set. I want to find a small subset of it such that later on, for any query, we are again preserving the cost with respect to that center set. But now the center is not just a single point, but rather a set of k points that are coming in our metric space. Okay. Any questions from the definition of k-center or a corset for k-center? Okay. Okay, so one again can see that a simple greedy algorithm produces a corset of size k plus 1 to preserve the cost of k center. Okay? And what is the greedy algorithm? It starts again with an arbitrary point, and for k iteration, it adds the point whose distance to the currently picked points is maximized. Okay, it's called the algorithm of Gonzalez from '85. And again, similar arguments shows that this also gives a constant factor approximation, but now for the case problem. So now, so far, I only assumed that my points are from a generic metric space. If I know additionally that the points are from some d-dimensional Euclidean space, then we can do some other techniques as well. For example, one of the techniques that people use in the context of corsets is to impose like a grid. In particular, again, if we know that the farthest distance between the points is roughly r, what you can do is to impose a grid of side length epsilon r. And now from each cell in this grid, you can just pick a single point. Okay. So the size of this corset would be 1 over epsilon to the d. It would give you an additive or error of epsilon r square root d. And for constant dimension, this would be a 1 plus epsilon approximation. Okay? So what if we want to go further than constant dimensions? Well, again, a similar technique to what I first described in the context of directional width works here. So first, suppose that all the points are on a single line. Okay, so a simple corset for one center would be basically to get to only keep 2 points that are at the most extreme ends of this line. Okay? So this preserves the maximum distances to all possible queries, and the query need not to be on the line. So even if the query is outside of this line, then only these 2 points preserve the maximum distances of this point set. Now, again, what you can do is that you can now put an epsilon net on all possible directions. And now for all the points we have, you can just project them onto the closest direction. And then for each of these directions, we just use our one-dimensional algorithm to keep a corset. So again, the size of this corset is 1 over epsilon to the d minus 1, and each point is dislocated by at most r times epsilon, so it gives a 1 plus epsilon approximation. Okay. So this is again for the one center in the Euclidean case. And now, what if you want to do k-center in the Euclidean case? Okay. So you can do the following. You can basically run an approximate clustering algorithm using the greedy algorithm of Gonzalez that I mentioned at the beginning. So maybe you run the greedy algorithm and it gives you this too. And then what you're going to do is to use one of the algorithms for one center to construct a one center corset. So basically, you can, for example, maybe impose a grid here and impose a grid here. And this would give you a corset, an overall corset of size k over epsilon to the d, or if you use the other data structure, k over epsilon to the d minus 1. Okay. Is the algorithm clear? Question? Okay. And in fact, this is one of this general kind of techniques that people have been using in the context of getting corsets for clustering problems. In fact, if you think about it, like one way, maybe one of the most intuitive ways to get a corset would be like that comes to mind is maybe we can do just naive uniform sampling, right? So the problem with this is that okay, maybe there are some small part of the data that are, very far from everyone else. So the cost or the value is coming actually from those ones. So if you do uniform sampling, you're going to miss these points. So what you would really like to do is that maybe you want to sample these guys with a higher probability and these ones with a lower probability. Okay, so you want to somehow sample the points with, proportional to the size of the cluster they lie in. Okay. Again, there's a problem here because sometimes because here we want to do, we want to find a corset for clustering, but now maybe we have to do the clustering first. Okay, so instead, what people have been doing in the past is that in many instances, like an approximate clustering would suffice. Okay, so a very crude approximation that is usually easy, one can get them, and then based on the even by criteria approximation is enough. And then based on this crude approximation, you can find out some sampling probabilities for the points and then sample the points based on those probabilities. I believe Christian has also used this in his work. Okay, so then a general approach would be find an approximate clustering and then sample the points based on their cluster size. Okay, so now let me tell you about one, again, generic technique for constructing corsets that's based on sensitivity sampling. Okay, so in order to tell that, let me start by, let me tell it in the context of corsets for K-median. So again, for K-median, you have a set of points P. You want to find a subset S such that for any, again, query, so here again, the query is a set of K centers. We are preserving the cost. And what is the cost? The cost is the sum over all the points, the distance of the point to their closest center. Okay, so in K center here, instead of sum, we had maximum, and now for K median, we have just the sum here. Okay, and basically here it's easy to see that one needs to have a weighted subset, right? Just preserving a subset does not preserve the cost because we're taking a sum, so we allow the corset to be actually a weighted sum of the points in the data set. Okay. And again, we want to approximate this cost within a factor of 1 plus epsilon by picking a small subset of the original data, and we allow it to be weighted. Okay, and this general sensitivity sampling theorem says the following. It says that let's pick the points randomly proportional to their sensitivity. And what is the sensitivity of the point? For a point P, we define its sensitivity to be the maximum contribution the point can have in the cost over all possible queries. Okay, basically relative contribution. Okay, so you look at all queries and you see how much this point can have contribution to it relatively, and you take the maximum. So this is going to be the sensitivity of the point P. And the theorem says that if you're sampling with probability proportional to the sensitivities, then the number of samples you need to take is going to be, and then it's enough to basically take samples, which is the VC dimension over epsilon squared times the total sensitivity of all the points. Okay, so what we need to do is that we need to bound the VC dimension, the total sensitivity, and that's it. So for example, in the case of K-median, this VC dimension, so in general, the VC dimension is roughly how much information, how much parameters you need to describe the query. So here we have K centers, each in dimension D, for example. This is going to be KD. And then we also need to bound the total sensitivity. For example, for median, one can bound it by a factor K. So this gives a corset of size K squared D over epsilon squared for the K-median problem. And basically, this sensitivity sampling works for cost functions of this form. So this is basically the cost function should be the sum over all the points that we have, some weight maybe that depends on the point, times the distance of the point to the query. Okay, so one instance of it is K-median, but the query could be more than a set of K points. Maybe it's just a single subspace of some dimension J, or maybe a collection of K subspaces, each of dimension J. Okay. So apart from K-median, this algorithm gives corsets for J sub, basically when the query is a J-dimensional subspace, or for projective clustering when the query is a set of K subspaces, each of dimension J. So this is basically when we want to see how our data fits into a collection of, for example, K subspaces of dimension J. Okay. And let me basically just mention the state-of-the-art results for what we know about clustering. I hope I have not missed any new results. So for K and Z clustering, so what is K and Z clustering? Basically, if we take, if our cost contains like the sum over all the points, the minimum distance of the point to the closest center to the power raised to the power Z. For example, for K median, Z is equal to 1. For K mean, Z is equal to 2. So this is for generic K and Z clustering. This is what we know. This is for the Euclidean case. And for Euclidean K means and K median, we know slightly better algorithms. And as you can see, there is still some gaps, so it would be very interesting to close these gaps. Okay. And I want to mention that basically there has been a large body of work to reach actually to these results. A lot of works by different people. It uses different techniques and so on. So if there is any questions from this part, let me know. Otherwise, I'll move on to the second part of the talk. Okay. So the second part is going to be on composable corsets. So composable corsets is a corset with additional composability property, meaning that the union of the corsets should be a corset for the union of the original data sets. So in particular, if we have suppose that we have, again, some optimization function, and then we have multiple data sets, V1, V2 to Vm. We want to find subsets U1, U2 to Um, such that if we take the subsets and take their union, the value of the function f over the union of the corsets approximates the value of the f over the union of the original data sets. Okay? So if we have this property, we say that our corset has composability property. And I'll tell you in a minute why this composability property is important, especially for the sublinear algorithm. So if we get again, similar to the corsets, if this approximation is by a factor alpha, we say that we have an alpha composable corset. Okay, so once you have a composable corset for a specific task, it automatically gives us gives us some algorithm for the same task in the streaming setting, in the distributed, like a MapReduce or MPC setting. We can get runtime improvement and so on. Okay, so basically, how do we get it? Suppose that we are in the, for example, MPC model. Okay, so our data is large. It's not all in one place. The data is partitioned over multiple machines. And if we know that the problem that we would like to solve at the end of the day admits composable corset, each machine can just compute a corset on its own data and send it to a single aggregator. Okay. Because the aggregator can just solve the problem over the union of these corsets. It's because of the composability property that the solution computed by the aggregator is a good approximation for the whole data. Okay? And because the size of the corsets is small, the total communication is low. And so why does it have application to streaming setting? So in the streaming setting, you can proceed as follows. You can basically divide, if you know that the problem you would like to solve in the streaming setting admits composable corset, then you get a sublinear algorithm for free here. So what you can do is that you can partition the stream of input into chunks of size square root n. And now once you see the points or the data in the first chunk, you start keeping all of them in the memory completely until the whole chunk arrives. And then you compute a corset and only keep the points that are in the corset and remove the rest. And then you continue with the second chunk. Once you get it completely, you compute a corset and remove the rest, and you basically continue it until the end of the stream, and at the end you just compute your solution over the union of these corsets. Again, it's because of the composability property that what you output at the end of the stream is a good approximation for the whole stream of the data. Okay, and this allows us to improve the space usage of the algorithm from n down to roughly square root n, assuming the size of the corsets is negligible. Okay, and basically, you can think about running this for multiple levels. So you can basically trade off the space for approximation. So instead of having just one level, you can have a tree of these corsets. So you can compute corsets of corsets and so on. So you can get maybe n to the epsilon space with a blow up in the approximation of like instead of alpha, you would have alpha to the 1 over epsilon. Okay. Again, it has had applications for runtime improvement, even in like a practical for practical problems. So when you have a problem, you have you have an algorithm that is expensive to run on the whole data. You can just partition it, compute a corset, and only run your algorithm on the union of these corsets. We've used it in the context of similarity search to basically answer, like, if given a query, given a search query, basically, how can we come up with a set of results that are all related to the query, but at the same time diverse. So we were using these corsets inside the hash buckets of a nearest neighbor search data structure. Now let me tell you some algorithms in the context of to find composable corsets for the diversity maximization problem. So what is the diversity maximization problem? We are given a set of objects, and the goal is to pick a small subset of them, a subset of size k, that has the maximum diversity, that is preserving the diversity of the original data set. Again, it has application in searching, recommendation system, summarization, and so on. Theoretically, we are given a set of n vectors and a parameter k. The goal is to pick a subset of size k with maximum diversity. And for a large, and I want to mention two things here. First of all, if you look at it, this problem does not make sense in the corset setting. Okay, it only makes sense in the composable corset setting. Why? Because if you just compute an optimal solution of size k, you're finding a corset for the problem. Okay, so but the problem makes perfect sense in the composable corset setting. Okay.
What is the notion of a query?
Again, one way to describe. So in the context of clustering, you had a query, but here we just have a function, optimization function, that we want to maximize. And this is what is the maximum diversity you can get by picking k points out of your data. And you want to still summarize it such that the maximum diversity you can get out of this small subset is comparable to the maximum diversity you could have gotten out of the whole data. So again, there has been a large body of work on finding corsets for diversity maximization. Again, some of these algorithms are like greedy algorithm of Gonzalez, local search algorithms, and some are more complicated. And I want to mention that here again, this bound is not among these. This bound is not tight. And for the purpose of this talk, I'm going to show one of the algorithms here, which basically relates the normal corsets for for the notion of k directional height to composable corsets for the notion of volume maximization. Okay. So the notion of diversity that we are looking at here is basically the volume. So the goal is to pick a subset of size k of your data that has the maximum volume. Okay, for example, if k is equal to 2 and you pick these 2 points, then this is the largest, then this is a parallelepiped with largest volume that you can get. Okay. So is the problem clear? So you have a set of endpoints. The goal is to pick a subset of size k that gives you the maximum volume. Okay, the volume of the parallelepiped spanned by those k points should be maximized. Okay, and again here, the goal is to find a corset for this problem, and we are going to show that some variant of local search algorithm would produce a corset of size of approximation factor roughly k to the k and size roughly k. Okay, so again, what we need to show is the following. We need to show that if we have some point set and we multiple point sets and we run local search on each of them to get a small subset, then if we take the union of these subsets, then the maximum volume one can achieve by picking k points out of the union of the subsets approximates the maximum volume you can achieve by picking k points out of the union of the original data sets, and approximation factor here is roughly k to the k. And so what is the local search algorithm? In the local search algorithm, you start with a subset of size k of the points, and as long as you can switch one point in the data set with a point, switch one point in the current set with a point outside that increases the volume, you will perform this swap. Okay? So maybe first you start with these 3 points. You find another point that if you swap it with this one, it increases the volume of the parallel pipette span by those 3 points. So you swap it. Again, you find another point, you swap it, and so on. So this is the algorithm. And we want to show that this algorithm gives a composable corset for volume maximization problem. And again, it's easy to make sure that this algorithm runs in polynomial time. So I'm not going into it. And in order to check whether changing Q with P increases the volume, it's enough to look at their distance to this to the subspace spanned by the rest of the points that is in the current set. So this is a k-1 dimensional subspace. So it will become clear now why I'm mentioning this. Okay. So this is going to be the proof. First, I'm going to show that the local search algorithm gives a corset, normal corset, not composable, a corset for the k directional height of the point set. So this is slightly similar to the directional width of the point set, which I defined at the beginning of the talk. Okay, and now we will show that any corset for local search, any corset for that approximates the directional height would actually give us a corset for volume maximization. So if we have an alpha corset for k directional height, we will get an alpha to the k corset for volume maximization. And these two basically would give us our result. Okay, so let's look at this k directional height problem. So again, similar to the directional width, we have a set of points P, and now we want to make sure that we want to pick a small subset of P that preserves the maximum distances to all k-1 dimensional subspaces. Okay, so take any k-1 dimensional subspace G and look at the maximum distance of all the points we have in the original point set to this G. So we want to pick a small subset of the data such that this maximum distance over this small subset is not much smaller than the maximum distance in the original point set to the subspace. Okay. So again, here instead of having a single direction, here we have a subspace of dimension k or k-1, and we want to preserve maximum distances to all possible k-1 dimensional subspaces at once. Okay, and we will show that this local search algorithm that out of n points picks only k points is able to preserve maximum distances to all k-1 dimensional subspaces at the same time. So it's basically a corset. It's producing a corset for k directional height of the problem. Okay. So how do we prove it? So again, we have a point set. We run local search. We get a subset of size k. And now we want to show that this is preserving the k directional height, meaning that if later on I take a k-1 dimensional subspace G, then the maximum distance of my points in the corset to G is not much smaller than the maximum distance of the points in the original point set to G. Okay, and the way for example, we prove it is the following. So suppose that this is one point in the original point set that has the maximum distance to this arbitrary subspace G. And let's look at all the points that are in the corset produced by this local search algorithm. So if each of these points have distance at most x to this subspace G, then we want to show that the distance of P to G could not have been larger than 2k times x. Okay? So therefore, giving us this approximation factor 2 times k. So the way we prove it is as follows. We take the subspace that is spanned by all the points that are in the corset, and we will project this point P onto this subspace. Okay, so let's look at this subspace. Because PH is a projection of the point into the subspace spanned by these points, we can write it as a linear combination of the points that are in the corset. And furthermore, because of the local search properties, we know that all the coefficients must have absolute value at most 1. Again, otherwise, I'm not saying it precisely, but otherwise, if this property was not true, at the end of the local search algorithm, it would have been better to change P with change QI with P. Okay, so once we have this property, then we can just use the triangle inequality. So because the distance of each of these points to the subspace is at most x, the distance of P of x to this subspace is going to be at most k times x. Okay, so it's the sum of k terms. Each of those have distance x. Each of the coefficients is at most 1, so the distance is going to be at most k times x. And again, using similar arguments, one can show that this distance is also at most kx, and therefore, again, another triangle inequality would show that the distance of P to this subspace is at most 2 times k times x, giving us a factor 2 approximation. Okay, so this basically shows that the local search algorithm that maximizes the volume gives a corset for k directional heights that has approximation factor 2k and size only k. Again, this is a normal corset, not a composable corset. And so now the second part of the algorithm relates a corset for k directional height to a corset for the volume maximization. Okay, so let's see how. So suppose that we want to show that. So suppose that we have multiple point sets V1 to Vm. Let's take their union, and let's take the union of their corsets as well. Okay, so these are the corsets that preserve the directional height of the corresponding point sets. And now let's look at the solution of the optimal solution of the volume maximization. So these are the 3 points that maximize the k points that maximize the volume from the original point sets V. And now what we can do is the following. I'm going to replace these points one by one with the points from the corset, such that at each iteration, the volume will decrease only a little bit. Okay. So in particular, I'm going to look at the k-1 dimensional subspace that passes through all the points in the optimal solution except the first point, O1. Okay. And now I'm going to replace O1 with the point from the corset that is furthest away from this k-1 dimensional subspace. Because I know that these corsets preserve the maximum distances to all k-1 dimensional subspaces, and in particular this one, this replacement does not decrease the distance and therefore the volume by more than a factor of alpha, okay, or 2k. And again, we do it, so we replace O2 with someone from the corset. In the same way, we replace O3. So we repeat this process until all the points in the optimal solution have been replaced with points from the corset. Okay. So again, at each iteration, we lost a factor of alpha. We repeat this process k times to replace all the points in the optimal solution. So we get an alpha to the k approximation factor. Any questions?
I might have a silly question, but so on the previous slide, when you were fixing this k-1 lean points, and then you were showing you have guarantee on this orange point, but your corset which chose the orange point did not maybe have green points, right? Because you were dividing the points into
so that point was from some point set, and even in that point set there was a point whose maximum distance to any k-1 dimensional subspace was comparable to this point.
I see. Oh, okay.
Yes. So there's an orange point in that particular subspace. Good question. Actually. Yes. Okay. maybe we are even better off here, because maybe now you can use somebody from some other partition, but even if we only allow it to be replaced with some point from its own partition, we are still having this guarantee.
Thanks.
Okay. Okay, so basically these two together give us the result we want. We show that if we just run the local search algorithm, it produces a composable corset for volume maximization with approximation factor k to the k. Okay, and recently we also showed that if you run the greedy algorithm, you would also get some almost tight approximation, give you a corset of size k with almost tight approximation factor with a reduction to the local search algorithm. So we basically showed some local property of the greedy algorithm, and therefore the same arguments applies to the greedy algorithm. Okay, so now maybe you might be asking that aren't all corsets composable? And the answer is no. For example, if you take the volume maximization itself, if you look at the solution of the volume maximization, it's actually giving you, and that can be solved in with an approximation factor of e to the k over 2. Okay, so just the solution of volume maximization. But now in the corset setting, we know that even if we allow in the composable corset setting, we know that even if we allow the size of the corset to depend polynomially on k, then you cannot get better than roughly k to the k over 2 approximation for the. Okay, so there's a gap here. And sometimes for the problems for which we have a lower bound for composable, in the context of composable corset, sometimes random partitioning helps. So if we assume that the points are randomly partitioned among different groups, so here we had no assumption on the number of point sets, no assumption on how they are partitioned. But if we assume that the points are randomly partitioned among these groups, then basically one can get algorithms that would not have been possible in the arbitrary partitioning case. Okay, for example, and these are defined for the first time for the coverage maximization problem. They're called a randomized composable corset, again, when the partitioning of the points is randomly, and they still have application in the, for example, MPC model, where the partitioning of the points is left to the algorithm itself, or in the random order arrival for in the streaming setting. Okay, where the data is coming in a random order. Yeah, so with that, let me conclude. So we talked about corsets, some of the variations, a flavor of the algorithms, and some of the techniques. We showed basically that composable corsets would give you algorithms for the same problem in other massive data models of computation, and saw some algorithms for the composable corset setting as well. So some questions would be basically, first of all, like to improve the current corset construction algorithms, and like find out what are other interesting problems for which a corset could have impact. Also, like for some of these problems that we have a lower bound, would randomization help to solve those problems? And like in general, like what would be some, so we have some corset setting, but like if you think about it, maybe if you allow the size of the corset to increase, then maybe you can get better approximation factor. So finding some trade-off between the size and approximation factor of the corsets would be interesting as well. So yeah, I would end the talk here, and thank you. Let me know if you have any questions.
We have time for questions.
So in the streaming model, you are saying that you want to partition the data stream into trunks and then compute the corset for each of the trunks.
Yes.
Is it possible that for each trunk, the data are like very different, so that I guess your guarantee is saying that you're able to compute a good corset for each of the trunks?
Yes, no matter what is your original data set, you can always reduce the size of the data set down to, for example,
Can you do something better, like approximating which data items are more similar to each other, and then?
Yeah, could be possible. Yeah, if you have additional assumption on the original point set, then maybe you can come up with better approximation factor for the size of the for this diversity maximization, the size of the solution itself is k. So you can't reduce the size to a smaller number, but you can improve the approximation factor for that some of those.
I have no familiarity with this, so I should not be really stupid. So is there any utility in assigning since you have a PSX corset, is there any utility in assigning each cortex to partitioning or the data points to a particular point of the corset by some order or something like that?
So in the MPC problems, for example, your partitioning is done arbitrarily. So is partitioning is left to the problem. So then maybe it becomes more in that regime. You're saying not random, right?
No.
Not arbitrary, not random, but maybe with some. So I haven't seen any work that considers that in the context of course.
So is there any? Do you see any utility in being able to? So assuming. So okay. Yeah.
So it has. So back to your question, it has application if you can come up with that, then it has application in the MPC model.
Okay. Yeah.
Any other questions?
Could you compare corsets with kernels, especially approximate kernels?
So these are all very similar. So the main property of the corsets is that they should be a subset of the data.
That's the only difference.
So this is the main property of the corsets, but kernels is not necessarily the same.
Any additional questions to Sepideh? Right, I think people are happy and they're also hungry. So let's stop here. Thanks again. And I'm